In this part, or in homework 5C, we're going to be doing this entire amazing paragraph. Isopropanol synthesis, internal recycle, and which is basically the degree of freedom analysis. So first, again, get this picture in your brain. So we will most likely be referring to it a lot. All right, let's see, can I even open another tab? No, it just searches it up. So C1 asks us to treat the reactor R distillation column D1 in the pair of azeotropic columns AZ. Just a heads up, this is the azeotropic column. All it means is that the alcohol leaves on one end, as its water will, and then the ether will go out the other end. And that's because I believe its ether is immiscible with water, and so it'll separate itself out. Anyway, as a 3-unit operations. And set up the material balance equations in vectors form for each. So it's just going to mean we're going to have a really big, so like each composition is going to have a vector, everything's going to be a array, so it's going to be a lot of vectors, a lot of unknowns. Sorry, excuse me. For a combined molar feed rate, for a combined molar flow of feed water and recycle water streams from the decanter and distillation columns, 12 times that of the alkene molar flow rate. And so what that means is the water that comes in along with the water that is recycled from the reactions, as again, this is from the homework 4B or homework 5B, but this has the equations on it. You can see we use water in one of the reactions, and in the other reaction to make the ether, water is actually produced. And so what's it saying is that the combined water rate from the decanter and distillation columns is 12 times that of the alkene molar flow rate, which is given from above. The AZ decanter mole fractions, which is saying the water, is that what it's saying? Yeah, the AZ water mole fraction, so that's saying the water in here contains this much alkene, this much alcohol, this much ether, and this much water, and respectively, which is just stating that, and mole fraction ratios for each of these components between the distillate bottoms and the distillation columns D1. Let's read that again. So it says, it talks about molar flow rate, molar fractions, and mole fraction ratios for each of these components between the distillate and the bottoms of the distillation columns. And that's because distillation columns are meant that a certain substance rises to the top and then moves on to the next tank. And so there's a specific equation, we're not going to say equation, there's a specific ratio between substances which will affect the rate at which things will move down, I believe. Between the distillate and the bottoms of the distillation columns, D1, so we're going to call this distillation column D1, and that ratio is going to be 110.5.2, I believe. And how many equations and how many unknowns can there be? So for the same feed and product specifications as in part B, which I will get to, calculate the total molar flows and the compositions of the feed bottoms and the distillate of the distillation columns, as well as the extent of reactions and total molar flows of the ether and alcohol product streams. And so what we're going to be getting into is we're going to have a lot of unknowns, which will then give us a certain amount of equations we can solve for, and a certain amount of unknowns we can set before, as I showed in homework 5A, you can only have a certain amount of variables set and unset before an issue starts to arise. And so then it also talks about calculate the distillate of the distillation columns in D1. So it's D1 rate, and then the rate from here, yada, 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 as well as the extent of reactions and total molar flows of the ether and alcohol product streams. Okay, so this sounds like a lot, because it is, but we're going to take it slow and steady. So first, what we want to do is we want to look at what I've done here. And so this is the same as before. We are going to be using range, and D2NT is a few other different things. And what we have here is numpy. We have imported root, as we're going to be copying from homework B2, as they have the same specifications. And we've also imported jacks. We've imported jacks as what we're going to be doing is going to be a lot of variables, and jacks is a lot more accurate than numpy is. And so jacks is also able to hold a lot more variables. And so we will be using numpy for arrays. I believe that might be the only thing. But we're going to be using jacks for when we do return values and we're solving for 0 and all that type of stuff, because it's a lot more accurate and gives it with such big with a lot of equations. We're going to have 17 equations, I believe, which means it's going to be easier for jacks. So first, let's look at, this is what we coded just recently in homework V2. And we're going to copy and paste this. And what we're going to do is we're going to make a dictionary, as we're going to be referring to these values a lot. So we're going to do E equals, okay, that didn't happen. E equals, I believe it's dot dict. And so we're going to start doing this, as what this is going to be doing is setting up these as to be referred to in other parts. And for our unknowns, I'll get to that, but we are actually what we are going to be doing is we are going to be setting up a range for them. That way, it'll catch any unwanted mistakes, and it'll also set certain values for when we're trying to do our very big calculations. It's easier on the computer, as my computer has issues. So what we have here is E alcohol, or the product or the rate at which alcohol is, and we don't know that. So what we are going to do is we're going to do range, which range we have an X value, a low, and then a high. All of our lows, every single one of our lows is going to be 0, as you can't get less than that. And if we have a negative array, it's going to be taking values away. And if we don't set it to 0, it could get pretty ugly. So our X value of our alcohol is 100, is what we assumed earlier. But we're going to use 50, just as it's a good even ground than 100. Then we're going to have 0. And now for our high, if you think about it, look at the equations here and here. We have our alkene plus water equals the amount of alcohol that we're going to create. However, as we said earlier, alcohol, as you can see here, water has a 12 times that amount. So what we're going to be doing is we're going to assume, with a good reason, that water is going to be not going to be the limiting reagent in this factor. And so we're going to be then putting the alkene rate, which is going to be, I'm not sure, let's see if we do E prop. No, let's not do that. E prop F. And, oh, I see what happened. I didn't actually get rid of that. I didn't put that in. So let's get rid of that. And let's just see if anything breaks. So it says that prop F is not defined. So, realizing, when I went through it, that our unknowns had to be above what was being called on, or it would have that error. And so now we can go down to our ranges. So we're going to call this as, we're going to assume it's going to be prop, or E dot prop, is it prop F over 2 as our extent of reaction, 0, and then let's see, then our max is going to be the E dot prop is the amount, so, max is 100. And so one thing I want to specify real quick is that if you see there's like updates going through, it's most likely I am deciding that I actually want to add these decimal places to make it known as an integer, as I forget about those a lot. So if you do see that change, I'm sorry. And so now our reaction 2, it is basically always going to be half at max, no matter what, of what we had the first time, of reaction 1. So we're going to just assume it's E dot prop F over 4, comma 0 dot, let's see, E dot prop F over 2. And so that should give us no issues. And so now we can go through and we're going to change this to D. This refers it to a dictionary, I do believe. So now, hopefully I can do D dot, and let's hope this doesn't break anything. So if it does, I'm going to be really sad. And then I'll probably have to take a break and figure it out. But what I'm doing is just referring to a dictionary, and instead of a vector, I'm not sure, let me see if I can change that to D. If not, I think I may have made an error. I'll have to check that again. But what we're doing is referring this to a dictionary. And that works. Perfect. So let's look at something real quick. So we do D2NT of E. We have a crap ton of values. And what these values are telling us are what E, or our dictionary, holds within. So it's all of our values. And this is very hard to read and very hard to do anything with. So our wonderful professor has a few different chemical tools we can use for this. And so let's start writing these out. So we have X naught, then we have X to NT, X to NT, we're going to do this as constant. We also have, what else do we have? We have wrap, and then X to unknown. X to unknown. So again, I got ahead of myself, and I want to explain what I'm trying to do here. So what we're trying to do is take our function as what we have here, MBS. We're going to wrap it, then take the root of it, as we're going to have more variables now that we're taking a dictionary. And then we want to show the unknowns and the knowns. And so we're going to do wrap MBS, and we're going to do X root MBS, comma X naught. And we're doing dot X to return X values. And you see we have an error of, okay, so there's multiple errors then. Numpy ind array, that's spelled wrong, but we're going to not argue with that. So what we realize here is that we don't need this as a vector, as we're pulling everything from a dictionary. So we can get rid of that and realize that then here we have that. So we're going to try that. So it says numpy and array object has no attribute of prop f. So we have d prop f, prop f, prop f. Must mean I'm missing something here. Or I was hitting undo, and I must have undone something important as I'm trying to find the issue. And it says in error 3, there's the feed, dprop d, d, d. And it says that d.prop f does not exist. And so let's look at prop f. Maybe it was the issue with that. It was not. Okay, so there were a lot of issues in the code that, looking back on, I realized and I had to go through and fix. And I took almost a complete rewrite. And so you see here, I've changed a few of the names, and this is just going through and making it more noticeable and more space in between. But I'm keeping prop F and prop Y, propylene or our alkene amount. And the first thing I realized is that it said there was no value. And what was happening was, when we're wrapping this equation, we're basically turning our list of our values into a workable array, or something that we can actually use to do math with. And from there, what I was getting was I was trying to take the root of MBS, or the equation that I had just wrapped. That way I could actually do math with it, but I wasn't using the correct value. And by not using the correct value, it created a lot of unnecessary errors in here that I spent way too long of a time trying to fix. And as you see here, these are the 4 values that we actually want to, from this equation, that we want to root out, which will then give us our values. And so we take the root, and it converges, and now we're going to show all of the unknowns that we have. So we know that the ether P, or the ether rate, is 9.27, the alcohol rate is 85.81, and then these are the extent of reactions between each of these functions. And all this is doing, for example, I'm going to get rid of this, those parentheses. This puts it in like one long line, and then doing this puts it in a list form, so it's easier for us to read. And the same here. This is just saying all of the unknowns that we've calculated above, and these are all of the constants that we were given or that we wrote down. So we've got our stoic amounts, the value amounts, the water X, the alcohol, the ether X, and so now that we have this, we should be able to start our calculations or our next step of calculations, which are going to be, oh, oops, let's see if this loads. Where's homework 5? So we're going to go to assignments. We are going to be doing the second, so what we just did was kind of the reaction based, and now we want to get what's going to be going into the distillation feed, and then what's going to be leaving and where it's going to be leaving. And so now we're going to go and start calculating these different steps. So as I called this MBS, we're going to call this MBS2. So we're going to define MBS2, and I believe we're also going to do is a dictionary. And now we can get started. We get to start our second set of equations, and what we're going to be doing is setting up a feed and a few other steps, like all the different balances and so forth. So we're going to have our, let's see, what did I name this above? So I named, oh, this isn't really named, so I'm going to call this reactor underscore feed, which is going to equal, let's see, what are we adding into the feed? We have all of the water and the alkene. So first, let's do the alkene amount. So we did prop F. Is that supposed to be P? Right? Let's see. Yeah. G dot prop F times G dot prop Y plus, and wait, that's, now we add the water amount, so it's going to be G dot water X times water F D dot water F, no, right? That's what I named it? Yeah. And so now, if you look at this, what we have here is a distillation column, and there's a certain ratio in effect that will determine and show you what goes up and what goes down. But so we're going to call the bottom and what comes out D1 bottom, and then we're going to call this the, oh, there's a name for this. Well, anyway, let's get to that after we do D1 bottom. So now we're going to do plus D, or D dot D, D1B, and then we're going to call that F times D dot D1B, and then we're going to call that X, or the composition. And then we're also going to add what we have here, oh, what's it called? A decanter. So we can call that the decanter water and the decanter amount, because the, let's see, something where it's given to us somewhere. The decanter mole fractions are given here, so we're given that at least. Plus, we're going to call that D dot decanter WF times D dot decanter WX, and that's the feed. And so now we want to do the reaction. No, okay, I already have that. So yeah, we have our feed amount of stuff that's actually going in. And now we want to do what's being taken in with the reaction, and then we want to do what's coming out, our products. So I know the product, so we're going to do this. We're going to call this D dot D1 feed. No, D1 feed, and this is because I'm calling it D1 feed, and because this is what's coming out of our reactor, and it's coming into our distillation column. And what we know about that's coming out of our reactor is that I believe we can do extent of reaction times stoic, or actually no, we're going to call this D1 D1 or D dot reactor. So my computer shut down again. And so what we're going to be doing, again, is calling this reactor underscore product, which should equal our distillation, d dot d1f x times d, what should we call it? So it's d1 flow x, let's just call it d1fx, and that's going to be the composition, and then d dot d1 f, and we'll call that y. We have our composition, and we can call that flow. And now we can do our reaction, which is just the incoming times the stoic. Let's look what we did up here. Yeah, I think it would just be extent of reaction times stoic. It would be the exact same thing. But we're not going to call this reactions. We're going to call this react RXN. It's easier that way. So now we have our general equations. Now we can start moving on to our distillation column. So our oh no, we have to do a reactor balance. That's going to be another one. We need to do a R balance, which is again basically reactor feed minus, or not minus, plus reactor RXN subtracted by the reactor product, and we want this to be 0. So we've got that. I'm not sure, I don't know if we need to dictionary these or not, but again, we'll learn. Oh, my computer's really loud. It's getting really hot. I'm sorry if this is a lot of clips cut together. I've had a lot of computer issues while trying to record this. So now that we have our reactor set up, we can start working on our distillation column. So again, we're going to call what comes out of here our D1 bottom. We're going to call here let's just call it D1 flow, D1F, as, well, what do we call the incoming? We call the incoming the D1FX, D1 flow. So, okay. So you can call this D1 top, theoretically. And so what we want to know is basically D1 balance is, again, D1 dot D1 dot D F1x times D dot D1 flow, as this is the incoming, minus, as that's the only incoming, minus, we're going to do, what do we call this? D dot D1 BF times, there's too many D's. That's my own fault, I guess. And then we want to also subtract the top amount. That's also leaving. Sorry, I'm kind of lost. This is where we last left off with the last clip. As again, my computer shut down as we were going through, if I remember correctly. So we were talking about the D1 balance, in which this is the bottom of our distillation column. And so now we have our inflow minus our bottom flow, which is leaving. Now we also need to subtract our flow that is coming off the top. So we're going to call that D1 dy, and we're going to call that D1 dy. Yep, and then we're going to call that D1 df, as these are the composition and the flow rates. All right, as nothing is actually updated, keep it like that and just keep ahead of things. And now we have that. Now we want to work with the water constraint. So the water underscore constraint equals, we're going to add all of the water flows together. So it's going to be d dot water f plus d dot d1bf as the bottom of the flow might be most likely is also going to be leaving as mostly water, hopefully. And then, oh, a mistake there, and a mistake here. Then we also are going to add our decanter water flow rate. So d dot decanter water flow. Can't spell. And now we're also going to divide this by the alkene rate, as again, that's the primary, divided by our d dot prop. I think it's uppercase P, prop F. And then, I want to make sure, okay, yeah, I think this will work. And then we're going to subtract by our water ratio, which we're going to call d dot wafer, our water alkene ratio constant, which is 12, as I'm not going to write that down yet, as we'll write that when we start doing, we update all of our variables below. So we have our feed, reaction, reactor product, reactor balance, and now we are also going to need to do our AZ balance, or our whatever our heteroazeotropic distillation. And so our AZ val is going to be our inflow rate, which is going to be d1 dy times d1 d, yeah, this. This is our inflow. And our outflow is going to be, let's look at this. It's going to be the water, the ether, and the alcohol. So we have the water, the alcohol, which should be, I'll just write that out myself. So it's going to be d dot alp times d dot alcohol x minus d dot ether let's see, ether x, ether p times d dot ether x. And this is the balance of this equation, right, of this right here. As in this topic, we have the only incoming flow we have is the distillation flow from the distillation column. Then we're going to have alcohol leaving. We also have water leaving from this decanter. And we have our ether leaving from this other tank that the decanter helps separate. So let's see, we have our feed, a reactor feed, reactor reaction, reactor product, and our reactor balance, which then leads us into our D1 balance along with our water constraint and our AZ val. But we're also missing there's a ratio or a volume liquid equilibrium that goes on within a distillation column, which is pretty advanced. However, we were given a simple equation and the ratio, which will help us solve it. And so you can see here, I kind of wrote down what we're going to be solving for. And so we have our D1 to Y, or our outgoing flow. Or this is our ratio, actually. And it should equal D1 dx over D1 dV. So this is the x value of the, actually I think we're going to change, I believe this should be x, but again, I will check later. I will check to make sure. Let's see, did I use that anywhere else? Yeah, it should be here. And so, but anyway, let's, before I mistake different values, we're going to call this D1 dy, and that equals our D1 dx over D1 dv. So d dot D1 dx divided by d dot D1 dv. X, or I just call it X to designate that it is a concentration or a molar fraction amount. So then we also going to subtract the ratio amount, which, let's see, what is it over here? And this is just the ratio components, and so it's D1. What should we call this? We're going to call this D dot D1 ratio. And again, I will most likely change these variables in the next clip, just so they're easier to understand. But now we have our reactor feed, reactor reaction, a reactor product. Okay, I'm trying to go through this. So D1 to Y is going to be what's coming out of the top. So again, I keep getting ahead of myself, and I want to explain real quick what we're doing. We are calculating each of these different unknown values, and then we're going to return them in a very long and a big array. That way we can start referring to these when we're trying to calculate certain unknowns. As what we're doing is setting up a dictionary so that whenever we have certain unknowns, we can plug it into our equations and we can solve them without having to retrofit it per equation. We're setting up on a specific basis. So this is what we're going to call the volume liquid equilibrium, and it's going to be D1 to Y, as I had earlier, which was right, and times the flow, and then this is our ratio over here, and then we're also going to change this to the D1 to Y, as this is the incoming, and so that's good, or at least it should be. So now let's do this, we want to return a array. So because, as what I stated earlier in the video, with JAX being a lot more accurate than NumPy, we're going to be using JAX array. So I think it's going to be NP, let's see, what did I import JAX as JAX.NumPy as JNP? So we're going to do JNP dot array. And we want to bring back a lot of these. So let's see, what do we want to bring back? And we want to add up a lot of these. But another thing we know is the water, let's see, where is that? Is this water constant at like the 12 times amount. And so because that's a constant, we're going to want to also bring that along with us, as it could affect a lot of the different variables that we will have inside of this array. And so this will actually give us another equation that we're able to solve for another unknown variable when the time comes. And so because all of these are arrays, you don't actually want to do an array, we want to do concatenate, and now we can go through our unknowns. So first we have RB balance. RB balance, then we have D1 balance, and then we have our DVLE, and then we're going to do our water constraint at the end, as that's something we're going to add at least one direction, as the water constraint should not have a lot of different variables. It should be very contained. So we're going to use AZBal. And then I believe we want to add inside, we want to do JNP dot underscore, or I think it's at least 1D. I'm not sure if it's supposed to be inside of this though. I think what we need to do is Control X, call it there, and then we can do JMP at least 1D, and do the wafer. I want to say we do the water constraint. No, we want to do WARC. Let's see, what's the issue? It's because it's not defined, but we will define it. So let's see. Yeah, so we're going to define that in our next step. However, what we have here is a very big return value of all the different unknowns we want to solve for. and it's within our function, so we can call on it when the time comes. So now we can start redoing our equation. So we're going to want to do, I think we're going to do e.dict again, and we'll grab these down here. And now we get to start with the fun part by changing a lot of the variables to within a range. That way, no matter which our variables are, even though we're going to start solving for the specific amounts and our specific values, we will have our actual different, we will be able to plug it in. So first, now we can do that WARC, the constant variable that we already know for the water is 12 as let's see. It says it is 12 times that of the alkene molar flow rate. So I think it's going to be 12 times the prop, as that's our alkene molar flow rate. Let's see. It says prop F. But okay, we'll keep it as that. And now we can start going through and creating ranges for our variables. Designate our unknowns that we calculated from this equation. So we have, again, as I was wrong, we actually want to set this as, this is going to be a constant for our function. So our WARC is going to be on here. And now we want to calculate D1, let's see, what was it up here? We had, I believe it was, we want to calculate D1F, the bottoms, the flow, and D1 dy. So let's start with E dot D1 D. Did we use flow up here? D1 df? No. So D1 df, and then that equals whatever is going to be up here, along with E dot D1 dx, and no. As let's see, did we get, yeah, we use that there. Okay, we called that flow instead of f, so we're going to call that flow. And these are both going to equal ranges, similar to what we did above, just like that. And then the next thing we have is going to be our bottom and our bottoms flow rate and constant. And some of these are going to be, most of these are going to be guesses, which is why we're going to put them in ranges. So we're going to have E equals D. We had D1 BF equals range. And some of these are actually given to us. So, okay. Oh, that's old. That's why. Let's see, what else do we have? We also have E equals D1 BX. So I'm just going to call these all as ranges until I calculate them or go and look through the homeworks. And then what else do we have? We also have our dy values, or D1 to y. E equals D1 dy equals range of that, E dot D1 dy. See, did I put, okay. I'm going to actually put flows on top. Just, I've been doing that consistently. So E, F, C, capital F, D1, D, let's see, yeah, D1, DF. That's going to equal range. And now we also have our, as we have this, everything here is going to be, we need to do our decanter, and we need our azeotropic. So, oh gosh. So we have A dot decanter water equals range, and E dot D water flow equals range. There's also a few things we didn't bring down that we are going to need to. And one more thing we're also going to have to describe is this D1D ratio. So let's do E equals D1D ratio. I just spelled it wrong. Yeah, no D. D1 ratio. That equals something. And then we have our extent of reactions we're going to want to bring down. I also think we're going to want to bring down these, but I'm not. Let's just bring down our extent of reactions for now. And what we're doing is calculating, or we're getting all of our values so that whenever we have an unknown, we can put a range and then shove it into this equation and it'll be calculated. So let's see, what are we given? So we are given that the decanter water mole ratio, so decanter ratio, Wx, is going to be NP dot array of 0.001, 0.001. No, it's an extra 0, wow. 0.1, 0.1, and then 0.8. So this is mostly water, very, very minimal amounts of alkene, and then equal amounts of ether and alcohol. Which makes sense. If they're being separated here, it'll be a decent amount that goes through. So we also have our, let's see, what do we have here? We have our fraction ratios. Yeah, so this is our, I believe this is our D1 ratio. So we're going to call that NP dot array, do 100, 10, 5.2. And then 0.2. And for the same feed, blah, 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 blah. So now we have to start calculating ranges. And, you know, as one does, we are going to have our guess, then we're going to have our low, and then we're going to have our high. And we're going to start and keep doing that throughout this, and then we can start actually calculating stuff, which is going to be exciting. Well, let's back up a little bit. I realized that this actually doesn't need to be on the outside. It can go inside of the array. So we're going to magically cut, comma, and paste this snazzy son of a gun. And then this is just an error because this hasn't been officially ran yet. And so now let's look at our D1 flow. And so this is the flow that is coming from our reactor and goes into our distillate, or into our distillation tank. And so our guess is just going to be the T dot, the alkene flow, so prop, not T, it's going to be E dot prop F anyway, multiplied by the water constant, as it's always going to be, you know, as it's always going to be, how many times? 12 times the amount? E dot WARC, and then our high is going to be dividing that by 2. So we're just going to and then not dividing, we're going to multiply it by 2. And then what we're going to have here is we're going to guess. So we're just going to guess. But so again, one more thing I realized when I was looking through this is that what we have here should actually be in the bottoms mole fraction category. It's just a small little mix-up when reading. And so now let's think of our D1 bottoms. So actually, no, before we do that, so this is going to be the top of our distillate, and this is going to be the bottom. So we're going to have the same guesses as our range. So for our bottom, we're going to say that we're going to assume it's going to be half of D1 flow, right? That would make sense, I would think. So E dot D1 flow. Oh, everything became, oh, that's why. Oh, so that might be it. Good enough. So where was I? So we were at here, D1 to flow, as this is what's going to be coming into our tank, or into our distillation column, and that, we're going to assume this is going to divide it by 2, as that's an easy assumption. Half is going to go down, half is going to go up. And then our high is just going to be, that's not what I wanted to do. Our high is just going to be this times 2, same as before. You know, why wouldn't it be that? Why couldn't it be if everything was perfect? And so now this is going to be, now let's do our bottoms. So now is, yeah, now let's do our the top portion of it. So the flow, D1 to flow divided by 2, that's an assumption, comma 0. And now, actually I don't like this. I'm going to put this above the bottoms, just so I can think of it as go in, top, bottom, next step. And now, same thing. I keep copying and pasting some different things. All right, and we're going to do 2 times E dot D1 to flow. Our range is going to be another guess. Let's just do this now. So again, the order is, it goes alkene or propylene, from then our alcohol, then our ether, and then water. So we're going to say there's going to be 0.05. All right, and then actually for these, it's not going to be a range. It's going to be an array. However, it's going to be a guess, but it can't be in a range within an array. So np dot array 0.0. Let's do it in even 1, so it's easy math. So that's how much alkene is left unreacted. From there, we're going to assume most of it is going to be water, not water. Most of it is going to be alcohol. So we're going to say 0.06. And then, okay, no, we're going to use 0.5 just for giggles. 0.06 is alcohol, which means then we're going to do 0.1. We're going to say is ether, as we know it's a very small amount. And so now we have 6, 7, 7.5. Now we're going to say 0.25 of it is water. And again, these are just guesses. These are estimations of some kind. And now, and that's the stuff that is coming in. So now for our stuff that's going to be leaving, again, we're going to say, oh, we're going to assume or guess that this is 0. Oh, remember, it can't be a range, it has to be an array. And I put guess. np dot array. Yeah, that's another issue. Don't forget to dot your T's and cross your I's like I do all the time. So now we're going to assume that this is the stuff that is leaving, as this is the bottom. So we can say 0.00, if that's 1, we're going to say that's 5. And while these should be very close to 1, you have to remember all the instruments you're going to be using to calculate these are going to be off. And so we can be very close, if not exactly to 1. You see, this is so small, it could be basically an oversight. 0.0005. And now, this is now in the alcohol that's going to be going up. We're going to assume the mole fraction is 0.0. Let's say it's 7, along with 0.0. 0.0. If this is 7, we'll say that's 1.5, not 1.5, 0.15. And then the amount of water that goes up, so that's 7, that's 85. We're going to say it's 0.10. You can't have more water than alkenes. That would be weird. So we're just going to say that's 7, that's 8, and we're going to say 15. Same thing as below. We have a very small amount that is just, we're going to say indistinguishable. All right. Let's see, what's the error? Anyway, I think it just doesn't read like that. Let's see. It says, perhaps I forgot a comma. 1, 2, oh, because I got zeros like that. That's better. So now we have our guess here. Now we can do our decanter W. So this is going to be our, I did it again, I want the flows above the mole fractions. It's just easier to read if it's all the same. So the decanter flow rate is going to be, is that given? Decanter water mole, decanter flow rate. Okay, so that's not given, which means we get to do 2 ranges, I believe. And so we get to do a range, and then we get to do a guess, similar to before. So this will be our np dot array. There we go. And our range for the decanter is going to be, so the y is what's coming into our tank. So let's see, what we should multiply, or we should just do d dot d1 df, as that would be a, and then we're going to divide that by 2, as that would be a guess, as that's the flow that's coming into the tank, or into this distillation column. And so we can assume that half of it, no, not half of it, will be going into the water. Again, when I'm making my guesses, I got mixed up a little bit. And I also got mixed up when making the ranges, well, just the amounts, actually. So if you think about it, we have a water constant which states that our water is 12 times more than our alkene amount, which means we're going to have a lot of water, which means we're going to have a lot less of alcohol, and then alkene, and then we're just going to assume this is like 0, 0, 0, 1. And now we do the same here. We also realize that I put D1 to flow as thinking, oh, that's going to be, it's going to go from top down, without realizing what we should be doing is just plugging in prop times this, as this is going to give us the more accurate number than just this giant range. So I'm going to be doing that real quick, just so it doesn't get mixed up and lost. So now we also have our D1 to Y, and we want to assume that most of the water has gone down. However, it's going to be a small amount that doesn't. So we're going to say that it's about 1/3 each, as we still had 12 times the amount than what we really should have had. And we're just going to say our alkene is going to be like 0, 0, 1. Again, something very minimal and small and easy to lose. Yep, there's another error of mine. And so again, let's replace our D1 to flow with our alkene and our flow rate multiplied by our water constant. And now for our decanter water, we're going to again say it's the exact same thing as our flow rate, is our guess, and 0. And then at maximum, it's going to be 2 times our value. And our array is, we're going to assume that this gets a lot of the water out, as that is its primary job. So we're going to do 0, comma 0, comma 0, comma 0, just so we're able to go through. So we're going to say it's 0.98, as almost all of the thing that is in that water route here, as in this water pipe, is water, as that's its primary job. From there, we're going to assume that it's 0.01. I'm going to say 0.05, and then 0.01. That doesn't actually add up. So we're going to say it's 0.01, and then this, actually I'll put 9. That way it might actually add up to what we want. And this is going to be 0.0001. Very small, very minimal amount. So now we have this. We have our, this, meaning our guesses, along with the ranges between the flows. Then we have our ratios, which is all written out and given to us. We also have our external values, and we also want to bring down, which I didn't do last time, our alcohol and our propanol range amounts, which we are going to put right down here. And there's no error. So now we get to do the fun bit of actually solving this equation. And using, I believe we use Jax, and we get to start in using our this function again as this function. As I've stated, well, I'm not sure if I fully went into detail about how inclusive this equation is and how useful it is, thanks to our wonderful professor, about how it allows us to have such a big amount of unknowns such as this, and it allows us to calculate all the different values. But now we are going to start calculating. Looking through this, I again realized why this was an error, that I am trying to add a constant to an array for no reason when I should be adding the water constraint. So that makes a whole bunch more sense when thinking about water constraint is in an array. So in this addition of at least one more array gives us an additional equation for us, or an additional variable that we're able to solve for, because we have an extra equation that we can shove numbers into. And so now we have our value. We want to do a wrap. So we're going to call this wrapped EQ2 equals wrap of MBS 2. Right, that's what I named it, MBS 2. Okay, and now we can do root. We're going to say x naught. Let's see, what did I actually put up here? Just check again. We put root. Okay, no, we're going to do. Didn't want to do that. Wrapped underscore wrapped EQ2, comma. And now we want to do, we have our x naught, now we want to do our method, or we're going to use Jacobian. As I said it earlier, it's a lot stronger. So we're going to do, I think it's Jax equals Jax.Jacobian. I'm not sure if there's anything else I need to add to that, though. That's what scares me. Yeah, so I believe there's a method I need to type here, but I'm kind of lost on what it is. So if we do, let's look up Jax.Jacobian usage, compute a matrix. Okay, that's what we're doing, a really big matricy. Okay, it's not the way I wanted to do it. Or let's just do type. Jacobian, look at that. Okay. We don't know the grade, so it's not, look at that. But again, we're going to take this to the root, which is, we're going to take that x, which will give us all of our unknown values that we're solving for. What we actually want to put in this Jacobian is just the wrapped equation, so it knows exactly what we're using. So wrapped EQ2. Oh, I need to have, didn't actually complete the, there we go. And so when looking through this again, I keep checking and realizing I made a few mistakes. I was putting NP array instead of putting composition. So the array is allowing us to see dictionary to name tuple, as it says on the screen. And so it's allowing us to name this tuple, which is a guess. And so we're able to calculate this in an array format as a named tuple. However, if we had put it in an array, that makes it think that we know this equation. And so it gives us what this turns out to do, it gives us too many unknowns and not enough equations. And so if you remember from our, if you remember from what we did in homework 5A, talking about, there's a certain amount of components, phases, eventually you'll get to the point where you have equations and you have variables. And you have to balance them very, very carefully. And so by adding this comp, this allows us to tip the scales back into our favor and allows us to have the max amount of components possible. So now we're going to print sol.x, maybe just sol. So this prints all of the x values that we have. So now we are going to do, let's see, I think it's x to unknown. Then we're going to do, sol.x. We're going to do dot underscore as dict. So I think we want to do is that. And what we have here is our answers for all of our different variables. So we have our D1 flow, we have our components in that form. So it says in the -1, which means it's very small. Let's go to e to the 0.01, which is very small. Very, very small, as we expected it to be. Decanter water, okay. And then our extent of reactions, which is I think it's very similar or almost the exact same. I don't remember. But yeah, we end up getting our variables. And so now we're going to do a quick one-over just to make sure, as this is going to be very jump cutty, as this video will be, just because of my computer issues while recording. And so we start off with this. We did this in homework 5B, except what we did is we created a dictionary, and so we can refer to these inside of our function, our MBS function. That way, when if we have any different variables that we don't know, all we have to do is change their function up here. We say, oh, put range for prop and then component for the x value, just a change like that. And then we wrapped it so we're able to deal with this equation, and actually be able to do math with this equation. And then what this does is just wrapped x naught. It just shows us the values that our function has, and then what those values are, we're trying to root out or get to 0. Then we get our value, we take the root of it, and we get our as dict and our number, or our numbers. We get our values, which, let's see, 9.2025. Yeah, it's the exact same, if not exceedingly similar. And then this shows us all of our unknowns, and then this shows us all of our knowns. So now we are going to do again with our MBS2, our next equation. So we have our reactor feed, which has our intake of the propylene in the water and then the recycled water. And yeah, oh, that's just the feed, okay. I thought it was what was going in, so I was confused for a second. It's all the different waters along with their mole fractions that all go in. Then we have the reaction, or what takes place inside of the reactor. We have our product. We have our balance in the reactor. We have our balance in our primary distillation column, or our first distillation column. We have our vapor-liquid equilibrium, which was given to us, we can calculate using this ratio. And then here we have the bottom, the mole fraction on the bottom divided by the mole fraction on the top, which is subtracted by the ratio. Gives us our equilibrium amount. We then have our water constraint, which is all the different waters divided by or added up to. These are all the rates, not just the components. Added up together, and we divide by our propylene amount or alkene amount, and we're subtracting that by our water constant, which states that our water is always 12 times the amount of the alkene in the system. And then this is the azeotropic distillation, in which we did the only thing that's incoming is from our first distillation column. And from the first distillation column, the only thing that comes out of that is the Y, or the top half, as the bottom goes into the water reserve line. And then we subtract the ether, the decanter water, and the alcohol. And these are all the components and the rates. And then we're returning these values. So this is 4, this is 4, this is 4, this is 4, and then this is 1. So we get a good 17 equations, and yeah, a good 17 equations, which I believe that's like our max amount. And then from there, we go through, we write down our same things we did above, but now we have our flows, and we have our comp here, which again, made a mistake, but it's really important to note that this is what allows you to guess instead of having our exact answers like we did above. And then we did, okay, our guesses based on what we think the rates will be. And I changed these up a little bit to make sure they would add up. But go through, blah, blah, blah. Same thing as above. This is given to us. This is our ratio for the VLE, the vapor-liquid equilibrium phase. Then we, again, go through these equations that our professor gave us, which allows us to do math, and actually do something with this chunk of data. We've provided it. We wrap it, so again, we can do math with it. And then we take the solution that way, because if you try to take the root of, here, let's just try this. We're just going to do root of MBS2, comma, x naught, just for giggles. It just says there's no array, which they're right. That's because if we do this, there's really nothing that deals with what we have here, as it's in a list, kind of like flat, and we want it to be kind of like this. And so what the wrap does is it allows that to take place. Then we get our solutions. This is, again, you read it and you're like, oh, I don't understand what this does or what this means. And so it's because we have it wrapped and we have taken the root, and it's just difficult. And again, we use Jacobian because it's a lot better at calculating these massive equations. It can handle a lot more variables. It's a lot faster, and it's just overall better, I believe, than NumPy. And then we do this. We use x to our unknown of solution.x.asdict. And what this does, it shows us all of the unknowns and what our solutions, and we plug that into the unknown function. And then this asdict just lists it as a list instead of as our dictionary / list. And so as you can see, as I just stated, we have all of our different variables. We have our flow rate, we have our flow rate, and so it's pretty consistent, especially with our external reactions and what we had with above. And so yeah, that is the end of homework 5C and the end of our MEB class. So I hope you enjoyed.